In this video, I'll talk about hypothesis testing for the mean in the case where we're not assuming we know the population standard deviation. Instead, we'll estimate the sample standard deviation and use that in our test. So this example data set is ratings from an airport, and our sample standard deviation from the data comes to 1.05. We have a sample size of 60, and our standard error is 1.05 divided by the square root of 60. Our sample mean from the data comes to 7.25, and we're going to do an upper tail test with the hypothesized mean being 7. So our null hypothesis says that the mean is less than or equal to 7, and our alternative hypothesis says that the mean is bigger than 7. Our test statistic is the sample mean, 7.25, minus the hypothesized mean, 7, all divided by 0.14. That comes to 1.84. And to calculate our p-value, we're going to use a t-distribution with n-1 degrees of freedom. So n is 60, so 59 degrees of freedom. And this function, it's kind of nice. It'll give us the upper tail area directly. That's what the RT stands for here, right tail. So this tells us that the tail area to the right of 1.84 for a t-distribution with 59 degrees of freedom is 0.0353. We're using significance level of 0.05, and our decision, as usual, is if the p-value is less than the significance level, then reject the null hypothesis. And 0.0353 is less than 0.05, so we reject the null hypothesis. If we wanted to use the critical value approach instead, then this function here will calculate the value of t for a t-distribution with 59 degrees of freedom that will have an upper tail area of 0.05. That critical value allows us to, again, reject the null hypothesis, because the decision rule, if we're using the critical value approach, is if the test statistic is in the rejection region above the critical value, because we're doing an upper tail test, then reject the null hypothesis. And 1.84 is bigger than 1.671, so we do reject the null hypothesis. So let's see how this works in Excel stat. So we'll do a parametric test, one sample t-test. We'll select our data. So our data is going to be the airport ratings. We'll do a t-test rather than a z-test. In our options, we're going to do an upper tail test against a theoretical mean of 47. And our significance level will be 5%. And away we go. Let's just check we got the same numbers we got before. So our test statistic, 1.841. There we go, 1.84. Our t-critical value, 1.671. That's this number here. 59 degrees of freedom. Our p-value, 0.035. See up here, 0.0353 to 4 decimal places. That's what we got here. And our decision, as the computed p-value is less than the significance level alpha, we should reject the null hypothesis. And it looks like the alternative hypothesis is favored here. The mean, the population mean, looks like it's bigger than 7. If I wanted to do a two-tail test here, all these numbers are the same. Standard deviation, sample size, standard error, sample mean, hypothesized mean, test statistic. Those are all the same. P-value now, though, because we're doing a two-tail test, is going to be the sum of the tail areas to the right of 1.84 and to the left of minus 1.84. And there's a handy-dandy function in Excel that will give you this directly. You just put 2t here instead of RT, which is what we had before for the one-tail test. If you put 2t, it'll give you that two-tail p-value, which is kind of nice. If you wanted to do it by hand, you could just multiply this by 2. Decision rule, same as always. If the p-value less than the significance level, reject the null hypothesis. But it's not in this case. 0.0706 is not less than 0.05. So in this case, we would not reject the null hypothesis. If we did the critical value approach, here's the formula for that. It's going to be the value of t that will have half of the significance level to the right of it. So 0.025 to the right of 2.001. And the decision rule is if this test statistic is to the right of that in the rejection region, reject the null hypothesis, but it's not. 1.84 is not bigger than 2.001, so we fail to reject the null hypothesis if we do a two-tail test for this example. How about lower tail tests? Okay, so for this data set, I think this is toys, orders for toys from retail outlets for a specific toy. And we're not assuming we know the standard deviation, so we're going to calculate it from the sample. Comes to 11.8. We have sample size of 25, standard error, 11.8 divided by square root of 25. Sample mean comes to 37.4 in this case. We're testing against a hypothesized mean of 40, and we're doing a lower tail test. So in our null hypothesis, we'll have that the mean is greater than or equal to 40, and in our alternative hypothesis, the mean is less than 40. Our test statistic is 37.4 minus 40, all divided by 2.36. That comes to minus 1.10. And our p-value, because we're doing a lower tail test, will be the tail area to the left of minus 1.10 for a t-distribution with 25 minus 1, 24 degrees of freedom. That comes to 0.1406. We'll test using an alpha of 0.05. So because the p-value is not less than 0.05, we do not reject the null hypothesis. So it looks like the alternative hypothesis is more, sorry, we do not reject the null hypothesis. So the null hypothesis seems more reasonable here. Okay. We don't have enough evidence to reject that null in favor of the alternative. Critical value approach. Here's our critical value, which for a low tail test will be the value of t for a t-distribution with 24 degrees of freedom that has a tail area of 0.025 to the left of it. Sorry, 0.05 to the left of it. We're doing a low tail test, alpha is 0.05. And that critical value is minus 1.711. Decision rule for a low tail test, if that test statistic is to the left of that critical value, then we would reject the null. It's not in this case, so we fail to reject the null hypothesis. So let's see how this works in Excel stat. So we'll do a one sample t-test. We'll select our data. We're doing a t-test. Our options are a theoretical mean of 40, but we're doing a lower tail test. So we have less than in the alternative hypothesis, significance level of 5. Let's see if we can match up our numbers. So there's our test statistic, minus 1.10. Where were we? Here we go, minus 1.10 for the test statistic. Critical value, minus 1.711, that's this number over here. Degrees of freedom, n minus 1, so 24. And the p-value, 0.1406 if I go to 4 decimal places. 0.1406, there we go. And the decision, as the computed p-value is greater than the significance level, we cannot reject the null hypothesis. Finally, if we did a two-tail test here, all these numbers are the same. First number that's different is the p-value. Because it's a two-tail test, it will be twice the one-tail p-value. And we can calculate it using this t.dis.2t function. Alpha 0.05, decision rule. If the p-value is less than alpha, reject the null. It's not in this case, so we fail to reject the null. Critical value approach. The critical value will be the value of t for a t distribution with 24 degrees of freedom that will have a tail area of half of the alpha. Half of the alpha in one tail, half in the other tail. So we have 0.025 in the upper tail, 0.025 in the lower tail, and the lower tail critical value minus 2.064. Decision rule, if this test statistic was less than that critical value, we would reject the null, but it's not, so we failed to reject the null hypothesis.